Hi, I'm Dr. Creasy, and this is the video for Module 1, Overview, Reliability, Load and Resistance Factor Design, and this is video 0, where we look at Campbell Chapter 1. Make sure you read Chapter 1 in Campbell, then watch this video. You access Campbell by going to Novel. You can see the video Accessing Books on Novel and search for Campbell Composites Processes. Composite materials, for the purpose of this course, can be categorized as all composites, and then they can be materials that are either reinforced with particles or reinforced with fibers. We're mainly interested in the fiber reinforced materials in this course, but particle reinforced materials are both large particle composites such as concrete and dispersion strengthened alloys. For fiber reinforced materials, we can either have continuous fibers, and the only way to have continuous fibers in a material in significant quantities is if those continuous fibers are well aligned. We can have short fibers that are discontinuous, and those can either be aligned or randomly oriented. As the alignment increases, the amount of fiber possible to place in the material increases. As they become more and more randomly oriented, the fiber volume fraction decreases. These images show you examples of reinforcements. The left image shows all glass, starting with glass microspheres. These microspheres can either be fully dense spheres of glass or they can be hollow spheres. Chopped glass fiber or woven glass fiber. And the weave pattern, here's a simple weave that's very stiff, or here's a kind of twill weave that's much more flexible. The weave pattern determines how well you can make curved parts from the fabric. On the right-hand side image, you see carbon fiber that's been turned into a tube through filament winding placement. In this course, we are primarily interested in laminated composites. Those composites can be made with specific fiber orientations that give the properties needed for the part. In this case, it's a unidirectional layup. You have 8 plies of composite material with all of the fibers running in the 0 direction. As we'll learn later, you can make materials into a quasi-isotropic layup by orienting the fibers in these patterns. If we look at the quasi-isotropic layup, we can observe several things about the way the fibers are oriented. First, if we find the midplane, we notice that it's symmetric. That is, it has a mirror symmetry. At the same distance from the midplane, we have fibers at the same angles. The 90s are matched, the plus 45s are matched, and the zeros are matched in their distance from the midplane. This makes this symmetric. We also notice that for every plus angle ply, there is a matching minus angle ply. This characteristic makes the laminate balanced. In this graph, we look at all the possible combinations of 0-degree plies, 45-degree plies, and 90-degree plies. At this point, we have 100% 0-degree plies. At this point, we have 100% 45-degree plies. What the author is trying to tell us with this chart is that most useful composites fall in this mid-range. There are special applications where you can have, for example, 100% fibers in the 0 direction. If you were making a tie that takes purely a tensile load, you would want all of your fibers to be in that load direction. Let's take a quick look at what fiber forms look like. First of all, there's roving. Typically, glass fiber is provided in roving for filament winding. It's a large package. The fiber is pulled from the center of the package to go to the machine and unfurls from the inside. It can have 1 to 5 toes. This is a fiber toe, T-O-W, and each toe has usually several thousand fibers. When woven into fabrics, fabrics can be combined by stitching to make preforms with complex shapes and specific properties. It makes it easier to place the preform into a tool so that resin can be added and the composite processed. Three-dimensional preforms are possible using special weeding and braiding techniques. Here's a simple example, a T-stiffener made with a preform. On the right, we see a complex preform that connects to components at a joint so that the loads can be transferred appropriately from one composite component to another. The advantages of composite materials tend to lie in high performance for structures that need a high specific strength or high specific stiffness or modulus. As you can see, the specific strength or strength per mass of composites can be quite high, especially for carbon fiber materials, and outperform titanium, steel, and aluminum, which gives them an advantage when you're looking at making things such as transportation structures that need to be low mass. Future automobiles will incorporate more and more composite materials as designers seek to make them more and more lightweight. Another way that composites have an advantage is through the relative structural efficiency. So if you look the efficiency of the material as you go from aluminum to titanium to carbon epoxy, the structural efficiency increases because it's easier to directly shape carbon fiber composites into the shape that you need for your design. You have much better control than is possible by machining aluminum or titanium. This completes video 0. Follow the schedule that you find posted on eCampus.